All right, guys, this is part two of going over the 2014 International Multiple Choice AP exam. And I think I misspoke last time. This is practice test number 5 on the practice test assignment, not practice test number 4. So you're good if you've practice test 4 would be a brand new test that you haven't seen yet. So this is practice test 5. So those of you that have done practice test 5, then you've seen this one before. All right. So anyway, let's jump into it. So we left off. We're on number 21. Okay. So for all these questions on this page, 21 through 24, we're referring to this system. So double arrow equilibrium questions probably. Notice they gave us a value of Kc. So they tell us Kc is 14.5. Remember, that means it's greater than 1. That means at this temperature, so 483 Kelvin, because we have a equilibrium constant greater than 1, the reaction is thermodynamically favored if they ask anything about that. They tell us this is a delta H is negative, they're telling us here, so we know it's exothermic. That means, remember, heat would be a product. So Le Chatelier's principle, adding heat would drive the reaction that way towards the left, and cooling it down, removing heat, would drive the reaction to the right. Just in case those questions come up, but those are the kind of the quick things to point out. Kq is greater than 1, so we know what that means. Delta H is negative, so we know what that means, and then we can kind of jump into our question. So, which of the following explains the effect on the equilibrium constant when temperature of the reaction system is increased? So we kind of just explained it. Remember, the only time the equilibrium constant changes is if temperature changes. So we know it's going to change. D's not right. If this question had asked what happens to the value of K if we did something else and we didn't change the temperature, then K would be constant. But so we're increasing the temperature from 483 to 650, and because it's exothermic, that's going to drive the favorability of the reaction towards the left. So it's going to be less favorable, so KEQ is going to decrease. So it's going to decrease, and the only choice that says decrease is C, and the reason is because it's exothermic. So choice C, because for every exothermic process, as temperature goes up, KEQ, KC, the equilibrium constant goes down. All right, so let's go to 22. A 1 mole sample of CO and a 1 mole sample of H2 are pumped into a rigid, previously evacuated container, but it's 2 liters. So remember, if you were making a rice chart or anything like that, you want to plug in molarities, and here's a case where moles and molarities won't be the same. So the initial molarity of CO isn't 1. Molarity is moles per liter, so the initial molarity is 0.5. The initial molarity of H2 is 0.5, just in case. Which of the following is true at equilibrium? All right, so if you only start with the reactants, the reaction has to proceed to the right to reach equilibrium. And we started with equal moles of this, but we're going to lose the hydrogen twice as fast as we lose the CO. So we know when equilibrium is established, we're going to have lost more hydrogen than CO. And since we started with the same amount, we're going to have less hydrogen than CO. So B would be true. And because KEQ is greater than 1, we're probably going to end up with more of this than anything else, more product than anything else. So CO being equal to CO. Now the amount of CO lost is equal to the amount of this gain because it's a 1-to-1 ratio, but we don't know if they're going to be equal or not. Well, we know they're not going to be equal because the equilibrium constant is greater than 1. But anyway, so choice B has got to be the right answer. Yeah, let's not waste any more time on that one. All right. So 23, a mixture of CO and H2 is pumped into the same container. The total pressure of the reaction system is 1.2 atmospheres at equilibrium. So we've established equilibrium, and then we want to know what is going to happen to the total pressure of the system if the volume of the reaction is reduced to 1 liter. So we half the volume. So remember, if we half the volume, that's going to double the pressure. And if the reaction couldn't adjust in terms of Le Chatelier's principle, then the answer would be double the pressure, the answer would be C. But because this is an equilibrium system, remember, that increase in pressure is going to shift the reaction towards the right here because we have less moles of gas. Remember, an increase in pressure by decreasing the volume is going to cause the reaction to shift towards the side with less moles of gas, which is here. And that's going to bring the pressure back down. Now, it's not going to bring it all the way back down to what it was, but it is going to relieve some of that initial stress. So the initial pressure, right when we make that volume change, is double, but then the reaction is going to adjust. And so when equilibrium is reestablished, it's going to be somewhere in between 1.2 and 2.4. So we know the answer is B there. Okay. And then 24, which of the following statements is true about bond energy? So remember, exothermic, that means bonds of the products are stronger than bonds of the reactants. Okay, more energy is released when bonds are formed. That's what a negative delta H means. More energy is released when bonds are formed, the bonds of the products, than required to break the bonds of the reactants. Okay, so it's not the energy absorbed is not greater, it's the energy released is greater. The energy released of the bonds and the reactants are broken is greater. No, because when bonds are broken, that doesn't release energy, that requires energy. The energy absorbed as the bonds and the reactants are broken is less than the energy released. That's the ticket, C. So exothermic reaction, more energy released for the products bonds forming than was absorbed for the reactants bonds breaking. So C, because it was exothermic. If it had been endothermic, the answer would have been A. Okay, B is just an incorrect statement because energy is not released when you break bonds, and energy is not absorbed when you form bonds. Remember, axing is taxing and forming is warming. All right, let's go to 25. All right, so this one, acid-base buffer system, right off the bat. Okay, so I have acetic acid and I have sodium acetate. We don't care about the sodium. Remember, it's usually just a spectator ion. So we have acetate, which is the conjugate base of acetic acid. So we have a buffer system, and we have equal amounts of the buffer system. Now, this question is asking all about, how does the buffer system work? So we add strong acid, so we attack our buffer system with strong acid, but the pH doesn't really change, right? So the buffer system's working as a buffer, okay? But they're asking, how does it work? So remember, H plus from the strong acid is going to react with the base of the buffer, which is acetate, and you're going to get more acetic acid. Okay, so in this case, they're not representing acid as H plus, they're represented as hydronium. So it would be hydronium plus acetate yields more acetic acid and water. So choice C. If this had been a strong base, they don't have the reaction. But if it was a strong base, it would be OH minus plus acetic acid yields water plus more acetate. Okay, but in this case, it would be choice C. Okay, buffer system, right? So this is what it would look like if they were representing the HCl as just H plus. Here they're representing the HCl as H3O plus, the strong acid. Remember, chloride's just a spectator. Okay, so let's go to number 26. All right, so we have this redox reaction, right? But in there, all this is about stoichiometry. So it's already balanced for us. They have the coefficients in there. We're good to go. It's just asking you the number of these ions that react must be equal to which of the following. So it's just making sure you can read the ratios. It ends up being choice A. The amount of this is 1/5 the amount of this, right? So 1/5 the number of iron 2+ ions. So choice A. All right. So just stoichiometry using the recipe. All right. So let's go to 27. So here we have absorbance versus concentration. We have a little data point that's not on the trend line, which means maybe a mistake was made. And so based on the other absorbance values, this must be, we must have done something that would make more light absorbed for this sample, all right? And so if you read the question, it says, which of the following is most likely the explanation for the variance of the data at zero point 0.6 molar? All right. So why was more light absorbed here? So which of these scenarios would cause more light to be absorbed in the colorimeter? And remember, colorimeter, spectrophotometer, same thing. All right. The cuvette into which this concentration was placed had some water droplets. No, that would dilute the concentration and you would get less absorbance. The cuvette was slightly more than the others. No, that wouldn't do anything. All right, so overfilling the cuvette's not going to do anything. Remember, it's about the length of the cuvette. If you used a longer cuvette somehow, then that would cause more absorbance, like a longer path length. The wavelength setting, no. If it was moved away from maximum absorbance, then you would get less absorbance. And so here's the deal. You didn't wipe the cuvette clean, so you had a smudge on there that absorbed some of the light, and you got too much light absorbed. So choice is D for number 27. Okay. Move on to the next one. So here we got a reaction, and we have the rate law. So notice that Y2 is not in the rate law, so they're telling us Y2 zero order. We have to choose a mechanism here that's going to show Y2 is zero order and X2 is first order. And so remember, you're only interested in the rate determining step and anything above it. So since the first step is the rate determining step, that's all we'll look at. So X2 is first order, and then Y2 only shows up afterwards. X2 is first order, and then Y2 shows up afterwards. So both these mechanisms seem to be fine. Both mechanism 1 and 2 are consistent with the rate law. There you go, C. All right. So that's kind of a tricky question, because, a lot of people are going to want to pick one or the other, but both, if you add all these up, it would get this reaction, and both mechanisms agree with the rate equation that was given, so it's all good. All right, for number 29, we need to find the equilibrium constant for this reaction. So we're thinking Hess's law, but with equilibrium. So what we have to notice is we have to double this equation. So if we double this equation and add it to this one, we'll get this reaction. But remember, when we double an equation, we don't double the equilibrium constant, we square it. So we're going to take K2 and we're going to square it, and then we're going to multiply it by K1, and that's going to give us K3, and we want to know if it's greater than 1 to see if it's thermodynamically favored or not. So so K1 times K2 squared, it comes out to be 2, so that its equilibrium constant is greater than 1, so it would be thermodynamically favored, and it's because that equilibrium constant, K3, for this reaction is greater than 1. All right, next one. All right, so here gives us a whole spiel about DNA, but all they want us to do is figure out which one of these diagrams shows true hydrogen bonding. And remember, one of your dipoles has to be from a Fon bond, H bonded to O, F, O, or N. Okay, so here's H bonded to C. Nope, that's not going to work. H bonded to C. Nope. This would be negative dipole to negative dipole, so that would be a repulsion right there. Here's negative dipole with a hydrogen, but the hydrogen's not bonded to one of our Fon guys. H bonded to H, no. H bonded to H, no. It's got to be D, so here we go. We got H involved in a Fon bond, so we got that positive dipole interacting with that negative dipole. So because one of the dipoles is part of a Fon bond, there you go, there's a hydrogen bond, and then there's another hydrogen bond. So the answer would be D. Okay. All right, moving on to number 31. All right, so we got PES, but notice it's not a full PES. It's just showing us a 1s peak for different elements. So notice the binding energy goes from high to low, which it usually does, so we don't have to sweat that too much. But that means these 1s electrons here are more attracted to the nucleus than these 1 electrons for Y, and that's going to, the only reason that's going to be is because, especially when you're looking at the 1s shell, there's no shielding. below it, it's got to be because X has more protons. So the question is saying it shows carbon and fluorine. Well, I know X has got to be fluorine because fluorine has more protons than carbon. So Px is fluorine, but we got to get the right reason. It's because it has a greater nuclear charge, right? More protons in the nucleus. So choice B. Okay. So if you're in a rush, you might accidentally choose A here because you know the answer is X is fluorine, but that's not the proper reason. And fluorine has a larger first ionization energy, so that's not even a correct statement. So anyway, moving on. Number 32. All right, so we have a balanced redox reaction, probably like a redox titration type question. Okay. So, yep, a titration and experiment. So remember, we did this lab. So we got hydrogen peroxide being oxide. Remember, the main thing here is as soon as you see H2O2, remember oxygen in H2O2 has a -1 oxidation state, not a -2. All right, so that's a tricky one. So let's see. At a certain time during the titration, the rate of appearance of O2 is 1 × 10⁻³ moles per liter per second. What's the rate of disappearance of permanganate? So remember, all we have to do there is take our oxygen's rate and multiply it by the mole ratio of what we want to get the other rate. So all we have to do is take this, multiply it by 2, and then divide it by 5 because it's a 2 to 5 ratio, and that'll give us the rate of disappearance for permanganate. So we multiply by 2 over 5, and we get D. That would be the rate of disappearance for the permanganate. Because we're losing permanganate at 2/5 the time we're gaining oxygen, right? Which element is being oxidized during the titration? So remember, this is the one where, hey, we got oxygen and a -1 here, and it's going to a 0 here. All right, the manganese is going from +7 here to +2, so that's reduction. The oxygen is going from -1 to 0. So it's the oxygen, and it's going from -1 to 0, so choice A for 33. So remember, memorizing that exception for H2O2 is going to be a big one. It's going to show up. It always shows up. It always shows up at least once. Okay. Which of the following best describes what happens to the pH of H2O2 solution as the titration proceeds? So here, hydrogen ions are a reactant. So as the reaction's proceeding, these are being consumed. So we're going to have less H plus in our solution, so the solution is going to get less acidic. So remember, that means pH increases. So as H plus ions consume, pH increases, because that means less acidic, so C. Okay, so the H plus is decreasing, but that means the pH is increasing, C. Okay. All right, next one. All right, the BF3 molecule is nonpolar, whereas the NF3 molecule is polar. So symmetrical, asymmetrical. Remember, and you should have these memorized. Just BF, boron with 3 things, trigonal planar, nitrogen, phosphorus, arsenic with 3 things, trigonal pyramidal. Boom. Okay, it's got a lone pair on here, asymmetrical, no lone pair on the central atom, symmetrical. So, so unlike BF3, NF3 has a non-planar geometry, right? Trigonal planar versus trigonal pyramidal. So there you go. D would be our answer. Okay. All right, so here we got this reaction going. We're given the equilibrium constant. And notice right off the bat, you see Q. So this is going to be comparing Q to K. Now notice you're in a 1 liter container. That means moles are molarity, so we don't have to do any type of conversion or anything like that. And it says, which of the following describes how the measured pressure in the reaction vessel will change and why it will change the way, okay, so you're starting with some of everything. So we got to figure out which way is the reaction going to shift to reach equilibrium. So let's understand, if it shifts this way to reach, if it shifts to the left to reach equilibrium, pressure is going to go up because you're going from 1 gas particle to 2 gas particles. If it shifts to the right, the pressure is going to go down as it reaches equilibrium because you're going from 2 gas particles to 1 gas particle. So if remember, if Q is greater than K, it shifts left. You have too many products, and you have to lose product and gain reactant to reach equilibrium. If Q is less than K, then it's going to shift to the right. Okay, so remember, Q is just the same thing as the expression. So you're going to do 2.5 divided by 1.5 divided by 1. No coefficients other than 1, so we don't have to worry about squaring or anything like that. Okay, so, sorry, switch this on. So QC would be equal to this. So QC comes out to be 1.7, and KC was 6.5. So Q is less than K. That means it's going to shift towards the products, but because the products have less molecules of gas, pressure is going to go down. So the pressure is going to decrease because Q is less than K. So the answer should be choice C for number 36. All right, so 37, notice we got a delta G that's negative, so it is thermodynamically favored. So consider the reaction above when equal mole volumes of N2 and H2, each at 1 atmosphere, are mixed in a closed container at 298, no formation of H3. So they're telling you when we mix the reactants together, the reaction is not occurring. And we want to know why. But the reaction, thermodynamics tells us the reaction is thermodynamically favored to happen. But remember, thermodynamics is not the study of how fast a reaction happens, it's the study of if it can happen. So thermodynamics is telling us it can happen because the delta G is negative. But if a reaction is supposed to be happening in terms of thermodynamics, but it's not, it's most likely because it has a high activation energy. So, yep, B, a high activation energy. There we go. B. So whenever they're talking about like slow reactions than normal or slower reactions than expected, because thermodynamics tells us it should happen, but it's not happening, the answer is always a high activation energy. And remember, what causes a high activation energy is strong reactant bonds, basically. And think about it, right? Nitrogen's got a triple bond. That's a strong bond to break for this reaction to occur. So this reaction's probably got a decent, a pretty high activation energy. Okay. Oops. All right. So let's go to 38. So we got our titration curve. Notice that the equivalence point here is above 7, so we know a weak acid was being titrated. That doesn't matter here. Remember, the equivalence point's at 20, so the half equivalence point's at 10. So the pKa would be here, right around 5. So I know they're asking me for the pKa, so I know it's either A or B. That's the pKa. And then we got to figure out the molarity of the NaOH that was titrating. So the molarity of NaOH required was 20 milliliters, because that's the equivalence point. And we were titrating 20 milliliters of an acid. So it took the same volume of NaOH as the acid we started with. So therefore, the NaOH has to be the same molarity. So the answer should be B for 38. Okay. All right, we'll go to the next one. 39. We'll finish up this page on this video, and then we'll come back for part 3 for the rest of the test. All right, so we got a heating curve, and it says how much energy is required to melt 64 grams of methane. Remember, methane is CH4, but they tell us that here. So the molar mass of methane is around 16. And if you think about this, back in the day when you had to do this without a calculator, you'd be doing 64 divided by 16 to get 4 moles of methane, and then it requires this much energy to melt 1 mole of methane, right? Remember, the first plateau is melting, the second plateau is vaporizing. So if we're talking about melting at the melting point, which is 90 degrees, we don't have to worry about heating it up to the melting point. We can just start at the melting point. So all we're doing is doing 4 moles of methane times that to get our answer. And so around 4, so 3.8. So 39 should be B. All right, there's our calculation. 64 divided by the molar mass of methane times the molar heat of fusion, in this case for methane. So if they had asked for vaporization at 110 degrees Celsius, then we would be using this value here, okay? This is asking which of the following best explains why more energy is required to vaporize than it is to melt. Basically, that's what it's asking. And remember, you're breaking all the IMFs, when you vaporize something. So choice A, okay? Choice A for number 40. The enthalpy of vaporization of water is 40.7. The enthalpy of vaporization of methane is 8.2. So remember, the more energy required to vaporize something means the stronger the IMFs that something has. So this is asking, why does water have stronger IMFs than methane? So methane is nonpolar with only weak London dispersion forces, but water has hydrogen bonding. So why does it take less energy to separate the methane molecules from each other than the water molecules from each other? It's because methane doesn't have hydrogen bonding that water does. So A, water has stronger IMFs. Okay. All right. So that'll take us to the end of part 2. We'll come back, finish up the rest of the test in part 3.